Okay, so first way, if you want, you can look at, probably the way I would do it is, I'm curious first if they hit. Meaning not if they hit, if their roads intersect. So here's the math on showing that the roads intersect. Okay, you can set the y's equal, you could set the x equals, you could do substitution, you can do elimination. Okay, so some of you might have focused on x equals and x equals, or some of you are so used to y equals, so you got the y's together. But you solve, you get y equals 2 and x equals 9, so they pass by for a fact at 9 too. And then I should probably say, and maybe hit. The reason I only said pass by there is up above I show that they don't hit. But this story here shows you that at 9 2, there's an intersection. So there's always going to be a concern if they hit or not. Okay? So at 9 2 is what we're worried about. Now let me scroll up and show you the work here. Lots of different ways to solve this. So you're really worried about when does x equal x and when does y equal y. And if it happens at the same time, there's a collision. So x equals x on the left at 4/10 or 2/5 or 0.4. So then one way you could do this is, could you plug in 0.4 to both of the y's? If you plug in 0.4 to both of the y's, you're looking to see if the y values are the same. They're not. What did I do? I didn't do it that way. What did I do? I set the x's equal. I set the y's equal. Do the x's equal at some point? 4/10. Do the y's ever equal? No. And in fact, it's kind of cool, and I'm going to show you this on the animation. What's true about the red and purple y's? 2 apart always. The purple is always 2 ahead or 2 higher than the red. So they will never hit. And let me show you this on the animation. Here we go. Let me move it. Let me put it on 0.4. What do you notice? The x's are the same. And there's only one spot where the x's are the same, because if you come from forever right and I come from forever left, there's one chance that we pass by each other. That's at 4/10. Now, if I click on the red and the purple, you'll notice that the purple is 2 higher than the red. And in fact, anywhere I go, the purple is 2 higher than the red. The purple is always 2 higher than the red, so they will never hit each other ever. Okay? How's that so far? So, my little acronym, nim, I don't know what it's called. But when you're looking for collisions, I want you to think of cars, and the cars are on the road. So the collisions, you're thinking of the cars, and that's parametric. And then when you're looking at just the intersections is in rectangular, because then you're just looking at the roads with no one on the roads. You don't care about them on the roads. That should have done a little cute thing. There it is. Okay. And then I really thought this was funny and no one laughed, so maybe it's not that funny. But if there is a collision, you need to call the parametrics. Like paramedics. Parametrics. Linnea. Oh, cool. Okay, so those of you that are watching the video, Linnea asked the question or the comment. I found out that down here there's an intersection at 9, 2. So what I did for the collision part is I plugged in 9 for x and 2 for y. And I plugged in 9 for x and 2 for y. And I went and found the times, and they're different. That's another way to do it. Because remember, you have an x equation, a y equation, and in that there's t's. So there's a lot of different ways that you can merge it. In this case, we just found out that the red goes through the story at 2. And the y goes through the story when? At 0. Or did I say the y? Sorry. The purple goes through the story at 0. And such. The times are different. No hit. Good with that? Now, because of time, we're not going to do this one, but I do want to zoom in on this story right here. Let me zoom in on this story. Oh no, we have an asteroid coming to the space shuttle. Here's the orbit. Oh no, oh no, oh, pew, collision. And did it hit twice? No. So, rectangularly, if you set the rectangular equations equal to each other, what are you going to find? Both intersections. The roads hit twice. And then what am I going to find out when I do it parametrically? How many answers are we going to find parametrically? One. There's one spot at 0 where they collide. Parametrically, when you set them equal or however you solve it, you will not discover the right one here because they don't hit. So remember, parametrically, it's actually looking at the dot moving, and they do hit at 5, 0, at time 0. But then the one later looks like red gets there before the orange. Let's say there is a hit, like there is. What's a couple different ways that you can avoid the hit? What could you change of either one? Keep the same paths, but what could you do to change no collision? Isaac in the back. Cool. So Isaac said, let's let one of the colors start at a later time. So right now we are showing at time 0 they hit. Imagine if I backtrack one, let's say half a second, and then I say orange, go. Red, wait. Red, wait. Don't go yet, red. Wait, wait. And if orange goes and then we wait on red and then we release red, do you agree they will avoid each other at the first hit? What am I now concerned with though? The second one, because who gets there first? The red. Do you guys agree? The red gets there first. So if I held him back a second, he might actually hit orange at that spot. So that's one method that they do when they're working on all the satellites. Oh, let's stall this one. Let's hit a pause on this one. Another way is you could speed them up. Could you have one go through the system quicker? Instead of delaying it, could you have one speed up its story? So if it's here, let's start here. I can say red, speed up real quick. Red, speed up real quick. If red speeds up, who gets to the first spot first? Red. And we already said red gets to the second spot first. So he just gets there quicker. But do you see how you have to, no matter what you tweak, there's still a chance that maybe one doesn't collide, but the other collides. So this is a good problem to solve, and I have it right here on the next page. Good with that? Yay? Okay. So a little summary. Call the parametrics with the collision of cars. And for the road map, you're just setting the rectangulars equal. No worries about Marauder's map or movement on the roads. I-76 clearly hits I-70. That's fine. It's then when you put the cars on it that we worry. Correct. So the question was, when do collisions officially happen in parametrics? It's when the times are the same. So I might be at one spot at time 2, and you might be at the same spot at time 3. We're at different spots. Or we pass through it at different times. But if you're there at 2 and I'm there at 2, then we're meeting up. We're having coffee. We're colliding. Yes. Okay. Okay, we're back. Okay, so next thing. Here, I'm just going to hit pause on the recording for a second because I just want us to take some notes. These are some basic formulas that we're going to use with the parametrics. So far, we have not done any calc. I've taught you what parametrics are. I've taught you the Marauder's map. I'm teaching you how to create a story on top of a road map. But all of that's been algebra with elimination and substitution. It has not been really derivatives and integrals and slope. It's been really just plotting points in time. So I'm going to hit pause here so you guys can copy some of this stuff down, and then we'll take a look. I'm going to scroll up too for a second. Okay, so in these formulas, you've done dy dt and dx dt. That's your projectile speed in the x direction and your projectile speed up in your y direction. Okay, so in that video the projectile video and animation on Desmos, I zoomed in on that triangle, and there's the dx dt and the dy dt, and then there's the speed. Last night's homework, I started with the speed, and you broke it down because I gave you the angle so you could get the green and the blue. So again, last night with the Peyton Manning football stuff, I told you, hey, I'm throwing at 100 feet per second at an angle of 45. And because of that trig, you could grab green and blue. But likewise, backwards, if I give you green and blue, you can go get me the speed. So if I gave you green is 30 miles an hour and blue is 40 miles an hour, anyone do that math in their head? 30 miles an hour for green, 40 miles an hour for blue, 50 miles an hour for red. And I don't need the angle. I could go get the angle if I wanted, but it's just Pythag. That's all the speed formula is Pythag. Some of you probably wrote it down like, oh no, this looks very hard and confusing because it is the square root of a blob squared plus a blob squared. It's Pythag. Okay? Then, next thing. If I tell you the speed of y and the speed of x, so the green and blue components, if you divide them, you're just going to get the slope. And when I say slope, I'm referring to the slope of the path, the slope of the road. The road on the map, I can tell you the slope of it. Because when you divide, you flip and multiply, and those dt's cancel, so you get the dy dx. Okay? So that's the slope of the path itself, back in rectangular. Okay? And then the last one here is the integral stuff. And down low, it looks overwhelming again. Some big integral of some square root of blob squared plus blob squared. You already wrote what that blob is, though, and I highlighted it in yellow. That's the speed formula. So I'm integrating speed over time. And this is the whole reason we take calculus, is because middle school, what's constant? Which color up there is constant? R. You're going 60 miles an hour for 2 hours. And then you go 60 times 2 is 120. That's that D equals RT. But the whole thing on calculus is I'm not going 60 miles an hour for 2 hours on cruise control. I can speed up, I can slow down, I can hit the gas, I can hit the brake. So it's more like I'm going 60 miles an hour for this millisecond, but now I'm going 61 miles an hour for this millisecond, and then 62 miles an hour for this millisecond. 30 miles an hour for this millisecond, and now I'm back going 45 and then 60, and it changes nonstop, and that's what an integral does. An integral collects all of those small distances. When you collect those small distances, that's the arc length. And I want to make sure you know that's the arc length. When I say arc length, when we have the path of the ball, it is not, I am not saying it's that length. I'm not saying it's how far the ball flew, how far downfield Peyton Manning threw it, how far the baseball player hit the ball. I'm not talking about that. I'm talking about, when I say arc length, I'm saying how far the ball went on its path. So you can find the length of the bend. You can find the length of that parabola. Linnea, question. Cool, good question. So the question was, we're so used to integrals finding area. How come this is not finding area? Think of a couple things. We've done this before, where we do pi r squared dx. And what are we finding here? Here we're finding volume. And the reason we're finding volume is this here represents area, which is like feet squared. And this here represents feet. So when I integrate it, I got feet cubed. So yes, we're used to area. Here's an area one. If I just give you fx dx and I integrate, that's area because that's in terms of feet.